Hello, this video will demonstrate how to use QGIS to complete exercise set number 2 in CE 3354 for fall 2024. On the screen is a remote desktop into a computer that has QGIS already installed, and I'm going to attempt to live go through the steps to do this particular homework assignment. If you're using ArcGIS, you're kind of on your own. This assumes that you have QGIS version 3.34, and I think it's about 0.7 or 0.8 now, installed and configured correctly. And I'm just going to go through the GIS workflow. Now, I already have a solution on the remote. That's mostly for me. I'm going to try to follow the same steps and create a second solution. So let's first take up the whole screen. And currently it's now connected to the remote computer. And you should be familiar with the problem. We're in the Hardin Branch Creek watershed, Concho County, Texas. For the time being, most of these red dots are of no consequence to you. The one we are interested in is right here. And these blue lines, someone else has drawn this on the map back when the delineation was being done by hand. And in this video, we're going to do it using a geographical information system. This town here is Eden, Texas. And what we're going to do in GIS is try to get a street map and get located roughly this same coverage, and then load in elevation data, and then use some tools to analyze and find the watershed that's contributing to this point right here, as well as determine the area of that. So the first step is we would have to launch our GIS, and I have it written right here, 3.34. Hopefully that's the right one. I'll know in a second. The name is Prizren. Yeah, this is the right one. And it takes a little bit of time to load on a computer. And it is very memory dependent. So if you're trying to do on an 8 GB machine what we're going to demonstrate, I haven't been able to get it to work. It works on a 16 GB. So here's the already worked answer. We're going to create a new one. So let's go ahead and save our project, and we'll call it Hardin Branch 2. Right now there's not much there to save. Next, we need to make sure that a couple of plugins are installed. So the two plugins that are important are SRTM, which means Shuttle Radar Topography Mission, from the NASA server. And to access this, you have to create an account on the NASA server. It will walk you through it. It needs a username and a password. Make something up. I think it has to use a real email too. So this one is installed and activated. The other one we need is Saga Next Generation, which is right here, processing Saga. The Saga acronym has a meaning. I'll let you look that up. The other one we need is coordinate capture, and this is necessary for the last step, which is to actually get the watershed. The OSM downloader I need for OpenStreetMap. That's what I'm going to use to start our base map. So coordinate capture, OpenStreetMap, processing Saga, SRTM, downloader, and then some of these other ones are built in and have to be activated, are automatically activated. You have no choice. So I think we have the correct tools, and over here on the left side is the processing toolbox. We can access the tools that way, also access across the menu on the top. You have access to the mighty internet and YouTube. There are plenty of YouTube videos on how to use QGIS. 90% of them won't do what you want, but you can get started pretty quickly. So I'm going to bypass that entirely. Our next thing is we need to set our OpenStreetMap layer. In my case, it's in a browser content called XYZ Tiles. If that doesn't work, you can access it using the Data Source Manager and find the data sets this way. Again, there are plenty of YouTube videos on how to do that. So I double-clicked on it, and it loaded OpenStreetMap, and it's now showing here in this layer part. I don't need the statistics right yet. And we, the human being, have to do a little bit of work and get zoomed into the right part of the country. Eden, Texas is right about here. Pretty good guess. There's Eden. And so the area we're going to need to work with is probably that. You'll notice there's this feature here that happens to be one of the SCS dams. There's another one up here somewhere that does not show on OpenStreetMap. And let's do a little bit of organization. I want to make sure I get the part. So this is the stream we're getting. It goes around over. I want to make sure I get this part down here. Okay, we'll do one more zoomation. I think that'll get the area that we need. Now obviously I have prior knowledge of what the area is, and if you're starting from scratch you probably have larger areas. Let me go ahead and save this. We've zoomed to Eden, Texas. I have notes to adjust the transparency, so we go into Properties, Transparency. You'll see why we do that in a minute. Pick a number you like. 50% I think is, did it actually do it? It ignored me. Okay, so you can see it's less resolution than before, and that's so that when we load in the elevation data, it can pass through this layer and we can see elevation and the base map. Next thing we need is to download the SRTM data. You can either use the downloader here, or we actually can access it directly from plugins. I think they both do the same thing. I'll do it from the plugin. And we're presented with this dialog box. We've already adjusted the area to be about right, so we're going to set it to the canvas extent. Essentially, it's the rectangle that's shown here. And then choose download, and we'll let it load the images into the program. And we'll go ahead and we can use temporary files because we're going to do some manipulations and not necessarily actually save the entire file. So my username's Hunter S. Thompson and my password is ... Choose the okie dokie and let it do its thing. Okay, it claims that's the area that we've downloaded, and let's verify that. Elevate OpenStreetMap to the top. That looks, well, we'll find out if I didn't get enough in a minute. I may have gotten a little bit too short on the north side. Okay, so we've now downloaded the SRTM. The next thing we need to do is say reproject the stitched raster. So now what I want to do is generate a raster. We'll clip raster by extent. The raster layer we want to do is, we'll use the combined one, which is already stitched. Clipping extent is the rectangle. We're doing this because to determine the area, it's got to work up and down hill, and the less data it has to process, the faster it will be. We'll find no data. Pick some weird number that will be obvious. Output data type, and I want to save to a file, and I'm going to put a 2 on this to distinguish it from the prior one. Obviously you won't have files in yours already. Press the Save button. Hopefully we've built the command correctly. Let it run, baby, run. Well, I might not have enough area. We'll find out. And now our actually this is not filled, it's just the clipped. Let's rename it. I don't need these anymore. Okay, so there is my elevation, if you will. It's in meters of elevation, and we can learn about the layer from the information dialog box. So it's a binary grid. There's 594 by 432. 594 columns, 432 rows. If you think of it, rows is top down and columns is left to right. They're signed integer. Anyway, I think that's the basic information about the raster layer. So we reproject. Now we need to reproject that raster. So we want to do projection, warp. We're going to take clipped. We want to send it to pseudo Mercator. That's approximately a Cartesian type coordinate system. If you don't do that, the following steps probably won't work. And we need to give an output file. No, resolution. I don't care about the resolution. And I do need to save it to a file. We will call that okay. Reprojected SRTM2. Now on your homework, you might want to use more reasonable file names. Okay, we'll use the SDAT data type. Hit save. And I think I have everything set correctly. That's the nearest neighbor. Hit the run, baby, run. That looks about right to me. We can check it. It doesn't visually look like it has changed any, but now reprojected. Coordinate reference system should be WGS 84, and if we look at OpenStreetMap, WGS 84, they're now in the same coordinate system. That's really important. So now we can remove the original clipped one. Ta-ta for now. This would be a good time to save our work. And now we ultimately are going to want to just work on the raster. Let's get to the area of interest. Should be right about there. And you can see some kind of shading like there. And we need to focus in this area. There's a pixel right about here, another one here, some other ones. I'm going to re-render it using a slightly different symbology. We'll use hillshade. We will run the sun from the lower right hand corner. Now at this scale it's not terribly helpful. Let's zoom out just a touch more, a touch more. Okay, remember the light is down here, and so if these shadows are showing, that's implying that this is lower than here, so we're going to take advantage of that and use that to help define where this river really crosses the grid. The key thing is we reprojected the grid. This is not the original data, so stuff gets moved a little bit, and all we're trying to do is get enough to figure out the watershed. So in Saga Terrain Analysis Hydrology, there is a fill sinks algorithm by Wang and Liu. So let's choose that. And we're going to take our reprojected as the input. We'll leave the default minimum slope. You can read on the internet what all that means. We're going to do put the word filled into it, SRTM2, press Save. Deactivate flow directions, deactivate watershed basins. That's all we need, and so we'll run. Now this one takes a little bit of time. So run baby run. Hopefully I don't run out of memory. By shrinking the size of the grid, we've reduced the amount of area that it has to compute. Each of those grid cells, we're going to find out, are about 32 meters by 32 meters. And I'm wondering if I might pause the video while it's doing its thinking. It might be wise. So I'm going to pause the video and I'll restart it when this particular dialog box gets to completion. It takes a couple minutes. Hello and welcome back. So it's now completed. Let me show you the transaction log. It hangs out here for a while, and then it tells me it created one band, it loaded reprojection, declared it okay, yada yada, blah blah blah, fill sinks, and it claims it took less than a millisecond, but that is not accurate. This is much more accurate. It took 1 minute and 20 seconds to do what is actually a fairly small area. And now it has completed, and we have a new map called reprojected filled. Let's turn off reprojected old. Move this down so that they'll render. And let me turn off the OpenStreetMap. And you'll notice something different. There's reprojected original. Keep your eyes in this middle part of the area. And reprojected filled, let's go ahead and render it in the same symbology. Hillshade. You'll notice all this washed out area, that's where our actual drainage is, or what we're going to use as the drainage. So we're going to pick points somewhere along here. Even though this is showing the bridges right there, we'll just pick one of these points and we're going to use that to determine the complete watershed drainage area. Okay, our next tool we need is the coordinate capture. Start the capture. And I'll go pick that point. And we need to access this picture of the grid right here. And I'll use the upslope area program. And you give it the x coordinate. The y coordinate. Give it the right grid to work with. Multiple flow directions. I think at this point we'll just use the defaults. So I have upslope area to bridge. I'll put the numeral 2 in it to indicate this is my second attempt. Go ahead and save that. And I think we'll find out in a second. Run, baby, run. This runs a little bit faster, but not super fast. I think less than a minute, so I'll just let the recording go. Okay, so now it's showing our upslope area. And if we zoom out, that is our watershed. And now we need to figure out the area of that thing. As presented there, we can't really do the area, but it's showing everything. Everything in black is a low number, and it's zeroing out at the high numbers. So we're going to go ahead and do a raster calculation, and we'll pick every number less than 10 or so to create a new boundary. Let me go ahead and I'm going to pause for a minute. I'm now going to create a new raster and attempt to get a binary raster from this one that's ranging from a little bit bigger than 0 to 100. So we're going to just take everything at 50 or smaller and try to make it into a 1. So we go to raster, raster calculator, upslope area to bridge number 2, less than or equal to 50. I'm going to send it to, call a binary layer. I'm going to call it 2. I'm going from memory here, so I don't exactly remember what I'm doing. Okay, so it gets that taken care of. Choose OK. It kind of worked the way I wanted it. So except for this little stuff right in here, let's go ahead and look at the properties of that. so we got a little bit of area here that's buggered up. We will deal with that in another time. Okay, so we want to get the area of USA binary 2. Probably the easiest way is to go and use a set of raster statistics. Not there. Raster layer statistics. Yeah, it did what I want, which is the sum of the area so now we need to go ahead and take advantage of that, and we'll just use Excel to do the second part. So at this point we have more or less generated a watershed outline, with the exception of what to do about this little area here, and I probably could have achieved a better thing if I'd used a different breakpoint other than 50. Okay, I guess I could go back and try that. And it's claiming that there's 58,475 is the sum of the number of ones, and so if we know what the pixel size is, we will be able to, I think it's Excel, where is it? Okay, here's a already built area calculator to get the area of the watershed. This is supposed to be the same watershed, but since we just did it with different numbers, let's repeat everything that's here. We need to know the width and height of the binary grid. So you would go here, properties, information, 559 by 476. So it's claiming the total pixels is 266,084. And it's telling it it's a 32.82. So there's our pixel areas. Piece of shit. Okay, pixel size, total pixels. And in our non-zero cell, I think that's all we need from this. So we have 58,475 non-zero cells, the area per cell, and that gives us the area in square meters, area in feet, area in acres, and finally the area in square miles. When I do this by hand, I get anywhere from 17 to 23 square miles, give or take. We'll go take a look at what the by hand ones look like. So the point is, we now have functionally delineated the watershed per se and also computed the area. And in a future homework assignment, we will actually go from a raster to a vector to get a proper boundary. And then once we have the proper boundary, we can have it lay in the topographically defined stream network, and that'll be used for the semester project to help you build your HEC HMS models. So this is the key part to using a GIS to help you delineate a watershed. As stumbling as it is when I'm talking, this is quite a bit faster than doing it by hand. Okay, let me save this. Actually, I guess I should save the tab sheet. This is SRTM2 based. Okay, so there's what we got in SRTM2, and let's repeat it with SRTM1. This part will be easy. So let me save that. Open. Okay, so there's SRTM1. You notice it's not struggling with that little bit. And although these are identical data sources, the processing for whatever reason is slightly different. So this is all the same work. The only thing I need here is so this is 662 by 567. And my pixel size 3206. And if you are into significant digits, you can use a whole bunch, and that way whoever your client is will know you're an idiot. Do some intelligent rounding as necessary. So the last thing we need to do is get the statistics to this file. So this has, nope, that's not the one I want. Raster layer statistics. USA binary, run baby run. Look at the output file. This one says there's 61, 368. Those are the non-zero values. So copy that. Paste that. And I get 24.34 square miles versus 24.30 square miles. So we get, for all intents and purposes, the same result. Slight variation because of how I instructed the thing to generate, in this case, this red area. You notice it doesn't have that blue area, because when this was done to 0 on binary, I think I choose the cutoff point at 10 instead of 50. That's a way to generate a watershed object sufficient for this homework assignment. So if we went back to our homework assignment and we're going to try to edit it, GIS would be the screen capture of the GIS that we've shown. probably we can look on this and see that the shape more or less corresponds to what you'd get if you did it by hand. And then for the drainage area, 24 and some change. Remember to save the project so that we can use it for future work, because we will have future work. Now let's take a look at what that looked like doing it by hand. I think I have it by hand. So the same background maps, and so when you're doing it by hand, you can see that someone's drawn these drainage networks by themselves and then created a boundary, and then finally counted the number of cells in an arbitrary grid to get the watershed area on this hand-drawn map. Now let's see if I actually had a good sense to write down. Okay, determine the drainage area computed by. Okay, so the main channel is 7 miles long. We'll get to that in another homework assignment. Oh, I'm embarrassed. Doesn't look like there's the actual answer. This is showing 17 square miles versus 24. And keep in mind the computer one is, actually let's see what it's picking up that the by hand didn't. Yep, we get that. It's got the right shape there. I suspect this is a consequence of counting squares by putting on the hand-drawn grid system. So we're 17 versus 24. What's that? That's 4 and 3. That's 7 divided by 24. It's 30% off. That's a little bit on the high side, but again, I suspect it has something to do with the counting. You also see that the computer is picking up some area in here that was not done in the by hand. And I suspect the computer goes more north than in the by hand. Alright, that would be how one would attack this particular problem using GIS. And then by hand you would simply print out the map and then make the hand calculations. For what it's worth, on something of this scale, if you have the maps, it's probably faster to do this by hand, but only slightly. The key difference comes when you have to do things over and over again. The computer is far superior in that situation. I'm going to exit QGIS. Save that. And if I can get back into the recorder, I will stop the recording.